So far, we've defined the Hermite polynomials in two different ways. On the one hand, through the differential equation, and on the other hand, through the generating function. Wouldn't it be nice to also show that these two methods are equivalent? And that's exactly what we're going to do here. So we're going to start from the Hermite polynomials defined by the generating function, and then show that they also satisfy the differential equation. So what's the strategy here? Well, we have defined from the generating function that the Hermite polynomials also satisfy a number of recurrence relationships. And then we're going to try and reform these recurrence relationships such that we can recover the differential equation. So what do we have to start with? Well, we have this recurrence relationship, for example, that's hn plus 1 x is equal to 2x hn x of x minus 2n hn minus 1 of x. And then we also have one involving derivatives, that's hn prime of x is 2n, the Hermite polynomial of one order lower. So what I suggest you do is pause the video and take the derivative with respect to x of this equation over here, the first equation, and then try to also use the second equation so that hopefully you end up with Hermite's differential equation. Okay, let's take some derivatives. We have for the left-hand side hn plus 1 prime of x. And then now we have here 2hn of x plus 2x hn prime of x. And then we have the final term, which is going to be minus 2n hn minus 1 prime of x. Okay. What we need is a relationship that only involves Hermite polynomials of a certain order. So let's try and get all of the terms here replaced by terms which involve the Hermite polynomial of order n. So for the one on the left, we have the derivative of the Hermite polynomial of n plus 1. But now we can actually make use of this formula over here and just change n by n minus 1. So that we can learn that the Hermite polynomial hn plus 1 prime of x is actually 2n plus 1 hn of x. So this is just this equation here, but replacing n by n plus 1. And then the other culprit here is this guy, because this is a Hermite polynomial of order n minus 1. But if we carefully look at this thing over here and that thing over here, you see that it's the same apart from the derivative here. So this term is actually the derivative of that guy over here. And because of the equality, that's also the derivative of the left-hand side. So this thing here, this fourth term, is actually hn double prime of x. And now we're in good shape because the only thing we have left are terms which involve the Hermite polynomial of order n. Okay, let's clean up some stuff. So first, the left-hand side, we have 2 times n plus 1 hn. But then over here, we have also 2 times hn. So if we bring this guy to the left-hand side, that becomes 2n hn x. And then we have 2x hn prime of x. And then we have minus hn double prime of x, which we can of course reorder a little bit to look more like the regular form of a differential equation. So we bring this thing to the left-hand side. We bring also 2x hn prime to the left-hand side. And then we have plus 2n hn of x. And what we've derived here is basically saying that the Hermite polynomial of order n satisfies the following differential equation: x double prime minus 2x x prime plus 2nx, which we know is the Hermite differential equations. So luckily, both definitions are in fact equivalent.